Feynman once noticed something strange. In a physics classroom, students knew everything. On paper, definitions were flawless. Formulas perfectly recited. Every exam passed. With high marks, he asked a question. Simple, direct. What does it mean? In reality, silence followed. They knew the words. They did not know what the words described. He asked again. Give an example from the real world. No answer. He changed the question. If light reflects from water, what happens? Silence again. They could define polarization precisely. Electric field oscillates. Single plane vibration, textbook perfect. But when asked what you would observe, they froze. Feynman later explained this in his memoir. Surely you're joking, Mr. Feynman. He said something clear. They passed examinations, but did not understand physics. That distinction mattered deeply, because physics is prediction, not recitation. If you understand a concept, you can use it, you can test it, you can see it. If you only memorize, you can only repeat. The students were intelligent. They were disciplined. They were successful by academic standards, but they were trained to perform correctly, not to connect symbol to reality. Feynman saw the pattern. Not just there, he had seen it. In American universities, bright students working efficiently, solving assigned problems, yet struggling. When problems changed, he once said, knowing the name is not knowing the thing. That was his point. You can define energy, momentum, electric field. But if you cannot explain what actually happens when conditions change, understanding is missing. He was not attacking intelligence. He was questioning method. What is rewarded shapes behavior. If exams reward recall, students perfect recall. If grades reward conformity, students conform precisely. That is rational, given the system. But science requires something else. It requires doubt. It requires testing. It requires asking, what would happen if this were true? He expected students to think that way. Many could not. Not because incapable, because untrained. They were trained to reproduce language exactly as written. Change the wording, confusion begins. Change the context, performance collapses. That troubled him, because real understanding transfers across context. It survives rephrasing. It survives new conditions. If light reflects differently, angle changes, medium changes, prediction should follow automatically. That is comprehension. Feynman valued that. Believed something simple. If you cannot explain in plain language, you probably do not understand. Not deeply. This was not dramatic. It was practical. Understanding feels stable. You can rebuild it from basic ideas. Without copying text, he often rederived formulas from scratch, not to show off, to check clarity. If he could not rebuild it, he questioned it. That habit mattered, because it protects thinking. From empty repetition, he saw education drifting toward performance, away from meaning. Students opted for what was measured. That is natural, but dangerous. If measurement misses understanding, understanding disappears. He did not say, education is evil. He said something quieter. Education can reward appearance of knowledge instead of knowledge itself, and when that happens, students look competent, but feel uncertain, because somewhere inside, they know the difference between repeating and grasping. Feynman cared about that gap between symbol and reality, between authority and verification, between grade and insight. That gap was the real issue, and he returned to it again and again, in lectures, in interviews, in writing, because science begins with honest doubt, and education sometimes trains certainty before understanding. That was his concern, not rebellion, not ideology, just clarity. If you claim to know something, can you predict what will happen? If conditions change, can you explain it without technical armor? Can you test it yourself? If not, something is incomplete. That was the lesson from that classroom, and it leads further to verification itself, which he valued even more strongly. Feynman cared about verification, not reputation. Verification. In 1964, he joined a committee in California. Science textbook selection. Millions of students. High-stakes decision. Publishers submitted books. Beautiful covers. Impressive credentials. University endorsements attached. Committee members discussed. Reputation first. Author background next. Institutional prestige. Very carefully. Feynman did something simple. He opened the books. He read the pages, line by line. He checked explanations. Do they make sense? Do they connect to observable phenomena? Or just definitions? He noticed something. Others were not reading. They were evaluating signals, credentials, endorsements, marketing language, authority markers, not content itself. He objected quietly. Should we not read what we approve? Time was limited. Trust experts. He kept reading. One submission arrived, mathematics textbook, well endorsed. Proper signatures included. Respectable publisher. Everything looked legitimate. The committee moved toward approval. Feynman interrupted. Fair to problem. They asked why. He answered plainly. The pages are blank. Completely blank. Except the title. They checked again. He was correct. No printed content, just empty paper. The endorsements were real. The signatures authentic. The reputation solid. But the book had no material. He later described this. Surely you're joking, Mr. Feynman. His conclusion was simple. No one verified. They trusted authority instead of evidence. That disturbed him deeply. Because science begins with checking, not assuming. If you do not look, you do not know. Credentials are signals, not proof. Endorsements are opinions, not verification. He believed something fundamental. The first principle is this. You must not fool yourself, and you are easiest to fool. That sentence mattered. It defined his method. Never rely fully on someone else's certainty. Check if possible. Test if possible. Recalculate if necessary. He practiced this consistently. At Los Alamos Laboratory, during the war, security rules were strict. Safes protected documents. Scientists trusted procedures. Feynman tested them. He tried combinations. He observed habits. He opened cabinets. Not to embarrass, but to demonstrate vulnerability. If something claims safety, verify the claim. If someone says impossible, try differently. He applied this mindset later as well. During the Challenger investigation with NASA, engineers believed the seals were reliable. Under expected conditions, Feynman asked one question. What happens in cold? He placed the material in ice water. It lost resilience. On camera, simple demonstration, not rhetorical, empirical. That was his style. Look directly physically. Reduce abstraction to observation. He was not anti-expert. He was anti-assumption. Authority may guide, but evidence decides. He warned about something subtle. Cargo cult science. He used that phrase in a Caltech address. California Institute of Technology. Experiments performed with scientific language, without scientific integrity. Form without substance. Procedure without doubt. Appearance without verification. That concerned him, because it looks rigorous, while lacking depth. The same risk exists in education. Students learn to cite, instead of test, to reference studies, instead of examine methods, to repeat consensus, instead of evaluating evidence. He believed something clear. Understanding requires participation. You must engage with the claim actively. Ask what would change if it were false. Ask what would happen under different conditions. Ask what predicts what. If you cannot answer, confidence is premature. He never claimed everyone must rederive physics from scratch, but he insisted on intellectual honesty. If you rely on authority, know that you are. If you have not checked, admit that openly. Do not confuse trust with proof. That distinction protects thinking. Without it, you become dependent on signals of credibility instead of evidence itself, and systems drift toward reputation management instead of truth-seeking. That was his warning. Quiet but firm. Verification is uncomfortable. It takes effort. It challenges consensus. But without it, science weakens, and education weakens. He returned repeatedly to this principle. Check the content, not the cover. Check the argument, not the author. Check the experiment, not the institution. That mindset shaped everything he did. It was not rebellion. It was discipline, intellectual discipline, and to curiosity itself. Because verification requires a desire to know, not merely to appear correct, which brings us to the third element, curiosity, and what happens when it gets replaced By performance goals, Feynman protected curiosity, very deliberately. At Massachusetts Institute of Technology, as an undergraduate, he noticed something. Students optimized for grades, efficiently, precisely. They studied past exams. They memorized patterns. They solved expected problems. Performance improved. Understanding varied. Feynman chose differently. He kept a notebook, not for assignments, for private exploration, problems not required, questions not graded, derivations from scratch, alternative methods tested, different notations invented. He wanted to see if the idea survived, without textbook wording, if he could rebuild from basic principles. Then it was clear. If not, something was missing. Professors sometimes advised, be more efficient. Use the standard method. Prepare for exams. He listened politely, then continued exploring, not for rebellion, for understanding. He later explained this. In interviews, said he wanted to know why. Not just how. Why equations worked. Why approximations held. Why assumptions mattered. That habit built flexibility. When problems changed, he was not trapped by one procedure. At Los Alamos Laboratory, during the Manhattan Project, he was young, many physicists older, more experienced. When standard methods stalled, he tried different approaches, sometimes inefficient, sometimes unconventional, but grounded in principles. He understood the structure, not just the steps. That distinction matters. Steps can be memorized. Structure must be grasped. If you only memorize steps, you freeze. When conditions shift, if you understand structure, you adapt. He valued that adaptability. It comes from curiosity, not compliance. Curiosity asks, what happens if? Compliance asks, what is required? Curiosity explores edges. Compliance stays centered. Curiosity tolerates confusion. Compliance seeks approval. Education often rewards correct answers quickly. Efficient completion. Clean procedure. Those are useful, but incomplete. If curiosity disappears, depth disappears. Feynman never argued against discipline. He argued against emptiness. Work hard, but know why. Solve problems, but question assumptions. Use formulas, but understand limits. He once said, science is belief in the ignorance, not disrespect. Humility. Even experts can be wrong. So remain open. Remain questioning. Remain curious. He demonstrated this publicly during the Challenger inquiry. With NASA, engineers believed risk was acceptable. He asked about temperature. He tested the material in ice water. Elasticity failed visibly. The lesson was simple. Nature answers honestly if you ask correctly. Curiosity asks correctly. Performance protects appearances. He preferred evidence over reassurance. He preferred clarity over comfort. That preference defined him. He won the Nobel Prize in 1965 for quantum electrodynamics. Shared with others, recognition followed. But curiosity came first, long before awards, long before prestige. He played with equations. Like puzzles, he explored diagrams, which became tools, later called Feynman diagrams. They emerged from trying to see interactions differently, not from chasing recognition, but from wanting clarity. That pattern repeats across his career. Interest first, status later. He warned students, do not fool yourself and do not prefer being impressive to being correct, because performance seduces. Understanding demands patience. If you study only for external reward, curiosity weakens. If curiosity weakens, flexibility declines. If flexibility declines, original thought declines. He did not romanticize ignorance. He valued knowledge deeply, but knowledge must connect to reality, must survive questioning, must endure reformulation. Otherwise it is fragile. Education can support this, or undermine it, if it measures only surface accuracy. Students master surfaces. If it encourages inquiry, students explore structure. Systems shape incentives. Incentives shape behavior. Behavior shapes thinking. That chain matters. Feynman's example shows an alternative path. Stay curious. Verify claims. Explain simply. Rebuild from basics. Test against reality. Admit uncertainty. Revise when wrong. These are not dramatic acts. They are habits. Small repeated habits. Practiced consistently, over years. He was not perfect. He made mistakes. He changed opinions, publicly sometimes. But the method remained. Honest doubt. Active verification. Persistent curiosity. If you combine them, understanding strengthens, confidence becomes grounded, not borrowed, and performance becomes a byproduct, not the goal. That is the difference between sounding informed and actually understanding, between citing authority and evaluating evidence, between memorizing tools and building them. Feynman chose the latter, repeatedly, and that choice is available to anyone. Not dependent on IQ, not dependent on status, dependent on habit. Ask what happens. If conditions change, ask how you know. Ask what would falsify. Those questions protect thinking. They keep curiosity alive, and they align education with science itself, which was always his real concern.